This talk is going to be about conditional dichotomy of Boolean ordered promise CSPs. This joint work with Josh Brakensiek from Stanford and Venkat Guruswami from CMU. So first, we start by defining CSPs. In a CSP instance, we have a domain that is finite containing elements 1 to q. And we have a list of predicates A1, A2, and so on, where each AI is a relation of arity ki from 1 to q. And in a CSP instance, we have n variables x1 to xn. And given a bunch of constraints using the predicates from these AIs, the question is to find if there is an assignment of 1 to q the domain to x1 to xn that satisfies all the constraints or not. And CSPs are like classic problems in CS. And like for example, we have 2SAT, 3SAT, 3-coloring, and so on. And the main question concerning CSPs is whether given a CSP such as like a 2SAT or 3SAT or like 3-coloring or and so on, can we solve it in polynomial time or not? And is there a dichotomy? Like given a particular, like every CSP in P, or otherwise it's NP hard? Towards this, like the Boolean case was resolved very early in 1978 by Shepard. And after a long line of works, very recently, the general domain case was resolved by Bulatov and Juk. And the key tool used in this is the so-called algebraic framework, where polymorphisms of the CSPs are analyzed. In this work, we study a generalization of CSPs called promise CSPs, where instead of one domain, we have two different domains with Q1 and Q2. Predicate has two different forms, AI and BI. AI is the strong form and BI is the weak form. So AI is a relation in Q1 of arity ki, and BI is in Q2 of arity, again, the same ki. So the reason why we call this strong and weak is because there's a single homomorphism H that preserves all the AIs and BIs. That is, if there is an assignment of arity ki, vector of arity ki that is in AI, if you apply this homomorphism H, the resulting function vector should be in BI. In particular, it means that if an instance is satisfiable when we viewed it as AI, is also satisfied as a CSP in domain Q2 when we view the constraints as BI. So like we can see that this generalizes CSPs because when Q1 equal to Q2 and AI equal to BI for all I, and H is the identity map, this is the same as traditional CSP. And the question is same as CSPs, but in the S case, there is an assignment from Q1 that satisfies all the strong constraints, VIs. And in the no case, even if we use assignments from Q2, we cannot satisfy even the weaker constraints. So this is like a promise variant where we somehow include the gap between yes and no case. To give an example, the classic promise CSP is this approximate graph curling, where given a graph G, the objective is distinguished between the cases that G is 3 colorable versus cannot be colored with 6 colors. So here the Q1 is 3, Q2 is 6, and the predicate is just X not equal to 1. So the formal study of PCSPs was initiated by Austin, Guruswami, and Hastav in 2017. And after that, there's been a lot of progress, both from an algorithmic view and also from hardness view. And similar to CSPs, the key question is again, is there a computational dichotomy? Like when can a promise CSP be solved in polynomial time? And is it true that every promise CSP is in P or it is NP? And similar to CSPs, again, the key tool is this algebraic approach and generalizing this approach to promise CSPs. So what exactly is this algebraic approach? So in this algebraic approach, we study these objects called polymorphisms, which capture the closure properties of solutions to promise CSPs. So for example, if you have a promise CSP gamma, and we define this n-array polymorphism of this gamma, which is a function from Q1 to the n to Q2, And for every predicate pair AI, BI, if you have KI vectors, so KI is the arity of AI and BI. So is that each column, so when we view V1, V2, and so on up to VKI, each column is in AI, satisfies a strong predicate. And when we apply the function to each row, f of V1, f of V2, and so on, the resulting is in BI. So somehow this function is like a closure property of the promised predicate. Like if you have a bunch of solutions satisfying the strong predicate, if you apply this polymorphism, the resulting function satisfies the weak predicate. So for example, if you have this 1 in 3 sat and not all equal 3 sat of promise CSP, Boolean promise CSP, a function of arity 7, which is like a threshold of like threshold 3, like threshold function where the function is 1 if the Hamming weight is at least 3. It's a promise CSP because if you have any 3 vectors where each vector has exactly 1, 1, if you apply the function to any 3 of them, the resulting instance will satisfy not all equal 3 sat. Okay, and polymorphism satisfy this key property called minor closed. Minor is just a function G, it's a minor of f if of arity n. If we just obtain G by identifying some variables of f together. So for example, if you have G of x1, x2, x3 is equal to f of x1, x2, it's x1, x1, x2, 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 x3, x3. So you have this function pi, which is a arity of a function from n to m. See here, arity of f is 7. So pi is from 7 to 3. And we obtain this minor with respect to pi by just identifying the variables of f according to this pi. And the key property of polymorphisms is that they are closed under minors. And CSPs, there is some other property called closed under composition as well. We can also compose polymorphisms in CSPs, but in promise CSPs, that is not the case. In promise CSP, we only have minor closed property. And some of the properties that are true for polymorphism in CSPs are also true in promise CSPs. In particular, this Galois correspondence holds, where the computational complexity of a promise CSP is fully captured by the polymorphisms that the promise CSP contain. And this has been extended to next level by saying that the identities satisfied by the polymorphism are also sufficient to capture the complexity of the promise CSP. And in particular, if there are more non-trivial polymorphisms, then we get algorithms for the promise CSP. And if there are few polymorphisms, only like a trivial polymorphism, then the promise CSP tends to be hard. So this is again, it's sort of a rough guideline. And the challenge is to identify where the line is, like which sort of polymorphisms give rise to algorithm, and when does lack of this polymorphism give hardness. And this talk is actually about Boolean promises, where you have domain like Q1 and Q2, both are Boolean. And recall that in CSP case, Schaffer's dichotomy theorem was proven long back for the Boolean case. However, in PCSPs, that is not true. We have only some progress towards Boolean dichotomy, but we don't really have a full dichotomy. In particular, we have the result saying that if there are symmetric polymorphisms of arbitrarily large arity, we do get algorithms. But and we also have dichotomy when the Boolean predicates themselves are symmetric. This is like the AI BI are symmetric, and that's pretty much it. And the question is whether like this can be generalized to arbitrary predicates. Like, is there a computational dichotomy similar to CSP for Boolean PCSPs? It's like a weaker question rather than like a general PCSPs, but even this is not known. So towards proving like this result in this work, we study so-called ordered Boolean PCSPs and prove a dichotomy for them. And first, we define these ordered Boolean PCSPs. So ordered Boolean PCSPs are Boolean PCSPs which contain this predicate pair AI BI, which is like x less than or equal to y. That is, AI and b are both equal, and the predicate is this two-ary predicate, which is true if like the first variable is less than or equal to second variable. So why is this interesting? The reason this is interesting is because this is the simplest non-symmetric predicate pair there is. So we are trying to take the symmetric predicate dichotomy to like a next step. And other reason it is interesting is because adding this predicate forces the polymorphism to be monotone functions. And we want to understand the polymorphisms in the monotone case before we understand the general case. And the study of this ordered piece is actually introduced by Barto and Peter. And in this work, we prove that such Boolean ordered PCSPs exhibit the computational dichotomy, assuming rich 2-to-1 conjecture. In particular, we show that if there are polymorphisms of gamma, where such that there are polymorphisms with shapely value arbitrarily small, then there are algorithms. Or equivalently, if it has threshold polymorphisms of arbitrarily large arity, it has polynomial time algorithm, else it is NP-hard. So I'll define this shapely value later. And this rich 2-to-1 is this conjecture recently introduced by Braverman, Cote, and Minzer that is closely related to unique games conjecture. Okay. So one example is this. So recall that we have seen this 1 in 3 set and not all equal 3 set. If we add the two more predicates, x equal to negation y, which is the folding is usually referred as folding in the CSP literature, and x less than equal to y, which is the ordered or monotone that we study. If we add these two predicates, we can show that the PCSP, resulting PCSP, does not contain threshold polymorphisms or arbitrary large arity. And by our result, then it is NP-hard. To start by discussing the algorithmic part of the dichotomy. First, define the shapely value of coordinate I for a monotone function f. Shapely value is a way to measure the influence of the coordinate in the value of the function. So it is similar to the traditional influence of Boolean functions. However, shapely value is defined only for monotone functions. So formally, we start with all zeros input, and then we can randomly flip one by one input to all ones. So like we pick a uniformly random permutation and we flip indices from 0 to 1 in that order. So we assume that f of all zeros is 0 and f of all ones is 1, otherwise the function is trivial. And in this random process, at some point, the function value flips from 0 to 1. And the probability that so the function value flipping happens when we flip the ith coordinate is the shapely value of the coordinate I for the monotone Boolean function f. Okay, and by definition itself, we can observe that sum of shapely values is equal to 1. We also use this notation of maximum shapely value, phi of f, which is the max over all I, phi of I. Shapely value was originally introduced in economics to study the relative influence of power of voting agents. So it was introduced by Shapley and Shubik in 1954. They actually got a Nobel Prize in economics for this idea. Why is it relevant for us though? And there are two reasons. One is that it's a specialized and very useful way to measure influence of monotone Boolean functions. And second, it's a very versatile measure. It has like combinatorial and also analytical interpretations. So coming back to the algorithmic part of the dichotomy, we recall the statement first. Every Boolean ordered PCSP gamma such that for every epsilon, there is a polymorphism f of gamma with phi of f is at most epsilon. And if gamma has such a property, then gamma can be solved in polynomial time. So we do this in two steps. First, we show that if polymorphisms of gamma contains functions of arbitrarily small shapely value, then polymorphisms of gamma also has threshold functions of arbitrarily large arity. And recall that symmetric functions of arbitrarily large arity implies that the PCSP can be solved in polynomial time. This is using the basic LP and fine realization algorithm of Brakensiek, Guruswami, Roshan, and Jibni. So all that's left is to show that if the polymorphisms contain functions of arbitrary small Shapley value, then the polymorphism also contain threshold functions of arbitrary large arity. The way we show this is by using a structural result of Kalai. So he proved that monotone Boolean functions with arbitrarily small Shapley value, which is exactly what we are studying, have sharp threshold. And once we have this property, we can prove that there is a threshold function of these functions with sharp threshold as a minor. Like we just take a uniformly random minor of a function with sharp threshold. Turns out that with high probability, the resulting function is a threshold function. So also recall that the polymorphisms of PCSPs are closed undertaking minors. So if it contains functions of sharp threshold, then the polymorphisms also contain functions of threshold functions of arbitrary large arity. And so by basic LP plus affine realization, they can be solved in polynomial time. Okay, we now discuss the hardness part of the dichotomy, which is the hard part. And recall the statement, which is that assuming the rich 2-to-1 conjecture, every Boolean ordered PCSP gamma with phi of at least lambda for an absolute constant lambda, then the gamma is NP hard. And the way we show this is using the standard label cover long code framework. So in the label cover problem, the input is a bipartite graph containing union of L and R. And for every edge on the graph, there is a constraint pi e, which is a projection function from sigma L to sigma R. Sigma L and sigma R are the alphabets of the vertices in L and R. So the objective is to assign labels from sigma L to L and sigma R to R to satisfy as many constraints as possible. And the constraint is said to be satisfied if just it respects the projection constraint pi e. And it turns out that this problem is very hard to approximate. It's even if we are promised that there is a labeling satisfying all the constraints, it is NP hard to find labeling satisfying epsilon fraction of the constraints for every small epsilon, for every constant epsilon greater than 0. First start with label cover instance and reduce it to a PCSP gamma. So how do we do this? For every vertex V in the label cover, we have a set of 2 to the sigma nodes is known as the long code of V, FV. Okay, and we had two types of constraints. One is this something polymorphism constraint where we ensure that for every V, FV is a polymorphism of the PCSP gamma. Two, we add this minor constraint. If there is an edge E in the label cover with constraint pi E, we say that FV should be a minor of FU with respect to this function pi E. Okay, so before going analyzing the direction, so a quick note on how do we actually add these constraints in terms of like a PCSP. So recall that we are reducing a label cover problem to a PCSP. So first of all, polymorphism constraints are essentially a PCSP constraints. We just add constraints saying that, oh, this should satisfy the PCSP, and like all of these like should satisfy the PCSP. And the minor constraints we enforce by saying that some particular pairs of variables should take equal value. This we can achieve in multiple ways. One is to just add equality predicate to the PCSP itself, or we can just identify the variables together. Okay, and now we analyze this reduction. Completeness is easy. Like suppose that if there is a labeling satisfying all the constraints, we just use this dictator assignments that will satisfy all the constraints of gamma. Note that dictator functions are always polymorphisms. So they trivially respect the polymorphism constraints. And since these dictator assignments satisfy the label cover constraints, they also satisfy the minor constraints. So the soundness is the interesting part. Suppose that there are these functions fv for every v, satisfying the polymorphism constraints and also minor constraints. Okay, our goal is to then show that there is an assignment to the label cover instance that satisfies like a constant fraction of the constraints. And the way we usually do this is by somehow identifying a set of coordinates S of V for every V. This is known as the decoding procedure with two properties. One is that these set of coordinates should be bounded. Like for every V, size of S of V should be at most a constant for every V in the label cover vertices. Second, they should respect this consistency property, where we say that for every constraint U to V, and with edge constraint being pi, pi of S of U, which is that you take all the elements in S of U and apply this function pi, take the union of the resulting, should have some intersection with the S of V. So here you have S of V is 2 and 3, and S of U is 2, 3, 4, let's say. Here pi of 3 is 2, so pi of S of U and S of V are intersecting. So this minor decoding is consistent. Okay. So once we have this this type of decoding for every F, we can just pick a uniformly random label to V from S of V. This will satisfy a constant fraction of constraints. Okay, and if for every polymorphism we can do these two properties, then the polymorphism gamma is NP-hat using this whole label cover long code framework. And this idea is used in many settings in PCSP so far. In our problem, we know that there are bounded number of coordinates with high Shapley value. So we want to use decoding based on Shapley value. So in particular, we know that every function f in the polymorphism has some coordinate with the Shapley value at least lambda. So we define this set S of V, which is that set of all indices with Shapley value at least lambda. So for every vertex V, this set is non-empty, and we also have the boundedness from the fact that sum of Shapley values of all the coordinates is at most 1. So this is good. However, consistency is actually not true if we use an arbitrary minor. In particular, there are functions fu and fv, such that fv is a minor of fu with respect to this function, which is like a very structured 2-to-1 function. However, in fu, the first two coordinates have very high Shapley value, and all other coordinates have little of one Shapley value. But when we take the minor, the coordinate 2 has high Shapley value, and 1 and 3 have little of one Shapley value. So this seems by little of 1, I mean you can generalize this to n inputs, and the Shapley value is like subconstant. So this seems a bit counterintuitive, but there are such examples. So Shapley value based decoding doesn't quite work. However, what we can do is that the Shapley value decoding works on average if we take uniformly random minors. So, and however, then this leads to the question, what about label cover instances where the edges are uniformly random 2-to-1 minors? It turns out that those instances have already been studied recently. And that is exactly the so-called rich 2-to-1 conjecture introduced by Braverman, Cote, and Minzer. But they say that a label cover instance where each edge is a uniformly random 2-to-1 minor, like if you fix a left vertex, the right like the edges corresponding to it are uniformly random 2-to-1 minors. Even for those instances, the problem is hard. Like basically, given a satisfiable instance, it's hard to find assignment satisfying epsilon fraction of the constraints. They also showed that it is equivalent to UGC when if we ignore the perfect completeness case. So, and our main technical contribution is that we show that the Shapley inference based decoding is actually consistent under uniformly random 2-to-1 minor. And given the whole framework so far, this fact will complete the proof that under rich 2-to-1, our hardness holds, like Boolean ordered PCSPs with Shapley value at least some constant have they are NP-hard. So to conclude, we have shown dichotomy for Boolean ordered PCSPs, assuming rich 2-to-1 conjecture. And there are a couple of open problems. First, can we go beyond monotone polymorphisms? And second, can we make our hardness result unconditional without using rich 2-to-1? Thanks.